Hello there, and welcome to the Sleepy Professor. I'm so glad you've found your way here tonight, because we're about to embark on a gentle journey through the wonders of our planet. Wherever you are right now, let this be your invitation to pause. Let the day's worries fade, the mental chatter soften, and your mind settle like dust motes drifting through evening light. Tonight, we're exploring Earth, the only home we've ever known. This blue marble spinning through space holds secrets more fascinating, more delicate, and more mysterious than most of us realize. From singing sands to glowing fungi, from trees that remember to rocks that breathe, our planet is alive with quiet marvels that will soothe you, surprise you, and perhaps change how you see the world. Some of these facts might gently reshape how you see the world around you. Others will simply wash over you like a warm tide, curious and calming. If this peaceful exploration brings you comfort or sparks your wonder, consider liking and subscribing. It helps other weary minds find this quiet corner of the internet, one sleepy soul at a time. But for now, settle in. Take a slow, deep breath. Feel your body sink into whatever surface supports you. And let's begin this tranquil drift through the remarkable truths of Earth. The Earth hums a note too low for human ears. Deep beneath your feet, the Earth is singing. Scientists have discovered that our planet produces a continuous hum, a low-frequency vibration that resonates through the crust and atmosphere. This tone sits far below the range of human hearing, at around 10 millihertz, roughly 15 octaves below middle C. The source of this planetary hum remains somewhat mysterious. It may come from ocean waves colliding with continental shelves, atmospheric pressure fluctuations, or even the slow churning movement of magma beneath the surface. Whatever the cause, the Earth never stops humming. It's been doing it for as long as we've been able to measure, a cosmic lullaby that plays on and on. This deep vibration connects every part of the planet, traveling through rock and soil beneath mountains and oceans. When you stand outside, completely still, you're standing on an instrument that's playing a note older than any song. Silent to our ears but constant, a reminder that the Earth itself breathes and sings. Some scientists believe that animals with better low-frequency hearing might actually perceive this hum, using it for navigation or sensing geological events before they happen. The discovery of Earth's hum came relatively recently, in the early 2000s, when seismologists noticed a persistent background signal in their instruments. At first, they thought it was interference or equipment malfunction, but the signal was everywhere, on every continent, constant and unchanging. The Earth, it turned out, had been humming all along. We just hadn't been listening carefully enough. Sand dunes can sing and whisper. In certain deserts around the world, if conditions are just right, the sand begins to sing. These are called singing dunes, and they produce deep, resonating tones that can last for several minutes. The sound has been described as humming, booming, or even like a low cello note drifting across the landscape. This phenomenon occurs when dry sand grains avalanche down the face of a dune. As millions of grains slide together, they vibrate in synchrony, creating acoustic waves. The size, shape, and moisture content of the sand all affect the pitch and volume. Some dunes boom with notes so low you feel them in your chest. Others whisper softly, almost musically. A few stay silent, their grains too irregular or too damp to resonate. Marco Polo wrote about these singing sands centuries ago, describing them as the voices of desert spirits. Local legends often attributed the sounds to jinn, or ghosts trapped beneath the sand. Today we know it's physics, not spirits, but the effect is no less magical. Walking through these dunes at dusk, with the sand humming beneath your feet, you feel as though the desert is speaking, slow and ancient, in a language older than words. The singing sands can be found in deserts across the globe. The Sahara, the Gobi, the deserts of California and Chile. Each one has its own voice, its own pitch and timbre. Some researchers have found that the frequency of the sound correlates with the size of the sand grains, a natural acoustic fingerprint unique to each dune. The desert, it seems, is not silent at all. It has always been singing, waiting patiently for someone to listen. Rivers can run backwards during earthquakes. Rivers flow downhill. That's a fundamental truth we learn early. Water follows gravity, seeking the lowest point, carving valleys and canyons as it goes. But during powerful earthquakes, rivers have been observed flowing upstream, defying gravity, if only for a moment. This happens when seismic waves travel through the ground faster than the water itself can respond. The riverbed shifts violently, pushing water backwards against its natural flow. For a few seconds or minutes, the current reverses, water piles up, and fish swim in confusion. Boats rock violently. Debris flows in strange directions. Then, as the shaking subsides, the river remembers which way is down and returns to its course. It's been documented in rivers across earthquake zones: Chile, Japan, New Zealand, California. Sometimes the reversal is brief, lasting only seconds. Other times, the river takes hours to settle back into its rhythm, sloshing back and forth like water in a bathtub. In extreme cases, the earthquake can permanently alter the river's course, redirecting it into a new channel, or creating waterfalls where none existed before. It's a strange reminder that even something as constant as a river can be interrupted, turned around, made to pause. The flow we take for granted is fragile, dependent on the stability of the ground beneath. But always eventually the water finds its way again. Gravity reasserts itself. The river flows on, carving a new path if necessary, persistent and patient. The sky has a color we can't see. If you could see ultraviolet light, the sky wouldn't just be blue. It would glow with patterns and colors, entirely invisible to human eyes. The sun emits a tremendous amount of UV radiation, and Earth's atmosphere scatters it just like visible light. But our eyes simply aren't built to detect it. We're missing an entire dimension of the visual world, a secret layer of reality that exists all around us. Many animals, however, can see this hidden layer. Birds use UV patterns to navigate vast distances and identify each other. What looks like a plain brown sparrow to us might appear brilliantly patterned to another bird, with UV markings that signal health, age, or mating readiness. Bees see ultraviolet markings on flowers, guiding them toward nectar like glowing runway lights. A flower that appears plain yellow to us might have intricate UV bullseyes or stripes visible only to pollinators. Even some fish and reptiles perceive this spectrum. Certain lizards have UV-sensitive patches on their heads, possibly helping them orient using the sun's position. Reindeer can see ultraviolet light, which helps them spot predators against snow and detect urine trails left by other animals. So while you see a clear blue sky, a bee sees a kaleidoscope. A bird sees a map written in invisible ink. The sky you know is only one version of the sky, a narrow slice of a much richer spectrum. Above you right now, colors bloom that you'll never witness, beautiful and invisible, painting a world beyond perception. It's humbling to think that we move through a reality far more complex than our senses reveal, like living in a room where most of the lights are wavelengths we cannot detect. Forests smell like rain before it falls. If you've ever walked through a forest before a storm, you might have noticed a particular scent, earthy, fresh, and slightly sweet. That's not just moisture in the air or your imagination. It's the forest preparing, communicating with the atmosphere in a chemical language older than human memory. Plants release oils and volatile compounds when humidity rises and barometric pressure drops. These chemicals drift into the air, mingling with the scent of soil bacteria called actinomycetes that become more active in moist conditions. The bacteria produce a compound called geosmin, which is responsible for much of that distinctive earthy smell. Together, these elements create that pre-rain fragrance called petrichor when mixed with actual rainfall. But even before the first drop falls, the forest is responding in other ways. Some plants begin to close their leaves, conserving water and preparing for the deluge. Mushrooms, which have been waiting dormant in the soil, sense the change and begin to swell, ready to fruit once the rain arrives. Tree roots shift slightly in the soil, anticipating water. Birds fall silent. Insects seek shelter. The entire ecosystem seems to pause, holding its breath. So when you smell that scent, you're inhaling a chemical conversation between earth and atmosphere, a language spoken in molecules. The trees aren't just waiting for rain. They're reading the signs, communicating with each other through that underground fungal network, and adjusting their biology in real time. It's a dialogue that's been happening for hundreds of millions of years, long before humans walked the earth. The smell is strongest after a long dry spell, when plants have accumulated the most aromatic oils. The first rain releases all of that at once, creating an olfactory explosion. Some researchers believe humans find this smell pleasant because it signaled the arrival of water to our ancient ancestors, a sign that streams would flow and plants would grow. The scent of approaching rain, then, is not just chemistry. It's a memory encoded in our biology, a reminder that we too are part of this ancient conversation. Glacial ice can be thousands of years old. In the deepest layers of glaciers, ice sits that was formed when humans were just beginning to farm, when mammoths still walked the earth, when the stars were arranged differently in the sky. This ice has been frozen for so long that it's become a time capsule, preserving air, dust, and pollen from ancient worlds. Scientists drill deep into these glaciers to extract ice cores, cylinders of frozen time that can be miles long. Each layer represents a year of snowfall, compressed over centuries into solid ice. The layers are visible, like tree rings, creating a visual record of thousands of years. By counting these layers, scientists can date the ice with remarkable precision. Trapped inside the ice are tiny bubbles of ancient air, perfect samples of Earth's atmosphere from different eras. When researchers melt and analyze this ice, they're breathing air from another age. They can measure what the atmosphere was like 10,000 years ago, 50,000 years ago, even hundreds of thousands of years ago. The ice reveals carbon dioxide levels, methane concentrations, and traces of volcanic eruptions that darkened skies across the globe. Particles of ash from long-extinct volcanoes sit frozen in the layers, marking catastrophic events. Pollen from forests that no longer exist drifts in the ice, showing what plants grew in regions now covered by snow. Even ancient bacteria and viruses have been found preserved, dormant, but potentially still viable after millennia of frozen sleep. The ice remembers everything, every drought, every storm, every shift in the wind. It remembers the gradual warming and cooling of ice ages, the rise and fall of civilizations, the changes in solar activity and cosmic radiation. And deep in Antarctica, ice waits that's even older, perhaps 1,000,000 years or more, holding secrets we've only begun to uncover. Frozen time, patient and silent, waiting to speak its truth. Some of the oldest ice on Earth can be found at the bottom of glaciers in Antarctica, where the immense pressure has kept it solid despite the slow flow of ice around it. This ice is so old that the air bubbles inside contain atmospheric compositions from a world completely alien to our own, a time before modern humans existed, when the climate, the landscape, and even the position of the continents were different. Some rocks grow and breathe. They are called stromatolites, and they've been growing on Earth for over 3 billion years. These layered rock-like structures are built by cyanobacteria, tiny microbes that trap sediment and minerals, layer by patient layer, year after year, creating formations that are part rock, part living organism. During the day, the bacteria photosynthesize, producing oxygen and forming a thin mat of living cells on the surface of the structure. At night, they rest, their metabolism slowing. Over time, minerals precipitate out of the water and settle onto the bacterial mat, creating a new layer of rock. The bacteria grow upward, following the light, and the process repeats. The result is a structure that grows perhaps a millimeter or two per year, incredibly slow by human standards but steady and persistent. Today, living stromatolites are rare, found in only a few places on Earth like Shark Bay in Australia, where high salinity keeps grazers away. But billions of years ago they covered shallow seas worldwide, great forests of these structures rising from the ocean floor. These humble, slow-growing mounds were among the first life forms to oxygenate our atmosphere through photosynthesis, paving the way for all complex life. The oxygen they produced initially bonded with iron in the oceans, creating the banded iron formations we mine today. But eventually, the oceans became saturated, and oxygen began accumulating in the atmosphere. This was the Great Oxidation Event, one of the most significant changes in Earth's history. It was toxic to many early life forms, causing a mass extinction, but it also opened the door for aerobic life, organisms that could use oxygen for energy. Without stromatolites, we wouldn't be here. They don't move, they barely change in a human lifetime, but they live, and they build, and they breathe oxygen into the world in a rhythm measured not in hours but in centuries. Looking at a living stromatolite is like looking at a living fossil, a window into Earth's deep past, when the world was young and life was just beginning to reshape the planet. Fossilized stromatolites can be found on every continent, evidence that these structures once dominated Earth's shallow waters. Some are massive, reaching several meters tall. Others are small and delicate. Each one represents millions of years of slow, patient growth, a testament to the power of tiny organisms working together across unimaginable spans of time. Lightning can turn sand into glass. When lightning strikes sand, the result is called a fulgurate, a hollow, glassy tube formed by the intense heat of the bolt. Lightning can reach temperatures of 30,000 degrees Celsius, roughly 5 times hotter than the surface of the sun. When this incomprehensible energy hits sand, it melts the grains instantly, fusing them together into glass. The lightning follows the path of least resistance through the sand, often branching and splitting as it travels downward. The sand along this path melts and fuses, and when it cools within seconds, it solidifies into a glassy tube. The result is a fragile, twisted sculpture of natural glass, often branching like a frozen root system, or a tree of lightning preserved in stone. Some fulgurites are just a few inches long. Others stretch several feet underground, following the path the lightning traveled through the sand. Fulgurites are found in deserts, beaches, and even mountain peaks, anywhere lightning strikes sandy or silica-rich soil. Each one is unique, a record of a single violent moment when millions of volts of electricity met the Earth. The outside is often rough, still coated with partially melted sand. The inside is smooth and glassy, sometimes with a hollow channel running through it where the lightning's energy was most concentrated. Some fulgurites are clear or translucent, others are opaque, colored by minerals in the sand. Iron creates green or brown tints, while other minerals can produce reds, yellows, or even blues. Collectors prize them for their beauty and rarity, but they're fragile, easily broken if not carefully excavated. Fulgurites are also found on other celestial bodies. Scientists believe they've been created on the Moon and Mars by meteorite impacts, which generate similar temperatures and pressures. On Earth, they serve as a reminder that destruction and creation are often the same event, viewed from different angles. Once the storm passes and the sand cools, what remains is silent, delicate, and beautiful, a frozen echo of lightning's touch. In some cultures, fulgurites were considered sacred or magical, evidence of the sky touching the earth. Today, they're studied by scientists interested in ancient lightning activity and by geologists who use them to understand soil composition and paleoclimate. Each fulgurite is a time capsule, containing information about the sand it was formed from and the atmospheric conditions when the lightning struck. Mountains are still growing. Mountains seem eternal, ancient, and unchanging. They dominate landscapes, their peaks rising against the sky like permanent fixtures of the earth. But in truth, they're still rising, pushing upward even as you read this. The Himalayas, for instance, grow about half an inch every year, pushed upward by the slow collision of tectonic plates. The Indian plate continues to crash into the Eurasian plate, crumpling the crust and forcing it skyward. This process has been ongoing for millions of years and will continue for millions more. The collision began around 50 million years ago, when India, which had broken away from the ancient supercontinent Gondwana, finally collided with Asia. The impact crumpled the crust like a slow-motion car crash, and the Himalayas began to rise. They're still rising today. Though the process is imperceptibly slow from a human perspective, this growth isn't smooth or uniform. The plates grind, slip, and lock against each other. Stress builds over years, decades, or centuries, until it's released suddenly in earthquakes. These quakes can lift or drop sections of crust by several feet in seconds. Then, the slow accumulation begins again. Everest is taller today than it was when Edmund Hillary and Tenzing Norgay climbed it in 1953, though only by a few feet, a tiny difference but real. Other mountain ranges tell different stories. The Appalachians in North America are shrinking. They've been eroding for hundreds of millions of years, worn down by wind, rain, and time. What were once towering peaks, possibly as tall as the Himalayas, are now gentle, rounded hills. The Appalachians are among the oldest mountain ranges on Earth, and they show their age in their soft, weathered slopes. The Andes are still growing too, pushed up by the subduction of the Nazca Plate beneath South America. The Rockies, the Alps, the Caucasus, all of them are either rising or eroding, their shapes changing slowly but constantly. The Earth is not static. It shifts, folds, and reshapes itself constantly, on timescales so vast we can barely comprehend them. Beneath your feet, continents drift at about the speed your fingernails grow. Plates collide and pull apart. Magma rises to create new crust. Old crust sinks back into the mantle to be recycled. The surface of the Earth is in constant motion, a slow dance that's been choreographed over billions of years. Above you, mountains slowly climb toward the sky, grain by grain, year by year, reaching for heights they may never fully achieve before erosion claims them once more. The ocean floor has rivers, lakes, and waterfalls, deep beneath the ocean's surface, where sunlight never reaches and pressure would crush most surface dwellers. There are rivers that flow, lakes that sit still, and waterfalls that cascade, all underwater. This seems impossible at first, but it's real, created by the peculiar chemistry of the deep sea. These features form when dense, salty water called brine seeps up from the seafloor. This brine can be 3 to 8 times saltier than regular seawater, making it significantly denser. Because it's heavier than the surrounding water, it sinks and pools in basins on the seafloor, creating underwater lakes with distinct shorelines. The boundary between the brine and regular seawater is so sharp you can see it clearly, like the surface of a pond. Sometimes this brine flows down slopes, forming rivers that meander across the ocean floor. These underwater rivers can be hundreds of feet wide and flow for miles, carving channels just like surface rivers do. And where the seafloor drops suddenly, the brine cascades over the edge, creating underwater waterfalls that plunge through the surrounding water in slow motion, tumbling downward in a dense, salty cascade. These brine pools are toxic to most marine life. The extreme salinity and lack of oxygen make them deadly. Creatures that venture into them often die, their bodies preserved in the heavy, oxygen-poor water, creating eerie graveyards around the pool's edges. But around these edges, unique bacteria and tube worms thrive, feeding on the chemicals released from the seafloor: hydrogen sulfide, methane, and other compounds that would be poisonous to most life. The largest known underwater lake is in the Gulf of Mexico, stretching for miles across the seafloor. It has waves, beaches, and even tides influenced by the pressure changes in the water above. Submarines visiting it have filmed strange scenes: a dark lake sitting at the bottom of the ocean, completely separate from the water around it, as alien as anything on another planet. It's an alien landscape, hidden in darkness, where water flows within water, and the familiar rules of rivers and lakes are rewritten. A secret geography, mapped only recently, still mostly unexplored, reminding us that Earth's oceans hold mysteries as strange as any distant world. Soil is alive with billions of organisms. A single teaspoon of healthy soil contains more living organisms than there are people on Earth. Bacteria, fungi, nematodes, protozoa, archaea, and countless other microbes live, feed, reproduce, and die in the thin layer of Earth beneath our feet. This microscopic ecosystem is one of the most complex and least understood on the planet. These organisms break down organic matter, recycle nutrients, and help plants grow. They form partnerships with roots, exchanging water and minerals for sugars produced by photosynthesis. Some bacteria fix nitrogen from the air, converting it into forms plants can use. Others produce natural antibiotics that fight off pathogens. Fungi extend vast networks of thread-like hyphae, connecting plants and allowing them to share resources. Soil isn't just dirt, inert material to be discarded or paved over. It's a living system, fragile and irreplaceable. It takes centuries to build an inch of topsoil through the slow accumulation of decomposed organic matter and weathered rock. But it can be lost in a single storm if not protected by plant roots. Erosion, overfarming, and development are destroying soil faster than it can be created, threatening the foundation of terrestrial life. The creatures in soil range from microscopic bacteria to larger invertebrates, like earthworms and beetles. Each plays a role. Earthworms aerate the soil as they burrow, creating channels for water and air. Their castings are rich in nutrients, essentially pre-digested organic matter. Millipedes and woodlice break down leaves and woody material. Mites and springtails graze on fungi and bacteria, keeping populations in check. The color of soil tells a story too. Black or dark brown soil is rich in organic matter, full of partially decomposed plant and animal material. Red or orange soil contains iron oxides, the result of weathering in warm, moist climates. Gray or blue soil often indicates poor drainage and low oxygen, where anaerobic bacteria dominate. Each color, each texture, each composition represents a different community of organisms adapted to their specific environment. When you walk through a garden or forest, remember, every step lands on a universe. Beneath the surface, life thrives in darkness, quiet, patient, and endlessly productive. The health of this hidden ecosystem determines the health of forests, farms, and food chains. Soil is not just the ground beneath our feet. It's the foundation of life itself, teeming with invisible workers that make the visible world possible. Clouds can weigh over 1 million pounds. Clouds look soft, weightless, and ethereal, like cotton candy drifting through the sky. But they're made of water, and water has weight. A typical cumulus cloud, the kind you see on a sunny afternoon, puffy and white, contains around 500,000 pounds of water. That's roughly the weight of 100 elephants, or 40 cars, suspended in the air above your head. Larger storm clouds can hold millions of pounds of water. A single thunderstorm cloud might contain tens of millions of gallons, all hanging in the sky, dark and heavy. So why don't they fall immediately? The answer lies in their structure. The water in clouds is divided into billions of tiny droplets, each so small that air resistance and atmospheric updrafts keep them suspended. They drift, swirl, and dance on invisible currents, too light individually to overcome the air's support. These droplets are incredibly small, typically 10 to 20 micrometers in diameter, much smaller than a grain of salt. They're kept aloft by updrafts, columns of rising warm air that push upward against gravity. As long as the updraft is strong enough, the droplets stay suspended. Only when droplets collide and merge, growing larger and heavier through a process called coalescence, do they overcome air resistance and fall as rain. Clouds are also constantly forming and dissipating. The cloud you see one moment isn't exactly the same cloud a minute later. Water molecules cycle in and out, condensing from invisible vapor and evaporating back into it in an endless flow. A cloud is less like a solid object and more like a process, a temporary shape made by invisible atmospheric forces. It's a visible manifestation of humidity, temperature gradients, and air currents, a sculpture made of mist. From an airplane, you can sometimes see clouds from above, and they look solid enough to walk on, like vast white plains stretching to the horizon. But step out onto one, and you'd fall right through, surrounded by nothing but fog. Clouds are illusions in a sense, solid from a distance but insubstantial up close, holding oceans in the sky, heavy and light at once, caught between earth and space in an eternal dance of condensation and evaporation. Some caves glow with living light. In certain caves around the world, the walls and ceilings shimmer with thousands of tiny blue-green lights, like stars reflected in still water. These glowing threads aren't electric, they're not chemical markers, and they're not reflections. They're alive. They're the larvae of fungus gnats, tiny insects that have evolved one of nature's most enchanting survival strategies. Each larva spins sticky silk threads from the cave ceiling, creating a curtain of dangling snares. Then, to attract prey, the larva glows bioluminescently. The light is produced by a chemical reaction, similar to that used by fireflies, involving an enzyme called luciferase and a light-producing molecule. Flying insects, disoriented in the cave's darkness, see the lights and mistake them for stars or an exit. They fly toward the glow and get caught in the sticky threads. The larva, feeling the vibration, reels in its meal like a fisherman, pulling in a line. The most famous of these caves is Waitomo in New Zealand, where thousands of glowworms create a starry sky underground. Visitors drift through in silent boats, the only sound the gentle lap of water, surrounded by living constellations. The effect is otherworldly, like floating through space or drifting under a bioluminescent sky. The caves are dark and damp, but the lights make them feel almost magical, transforming cold stone into something beautiful. These creatures, called Arachnocampa luminosa in New Zealand, spend most of their life in larval form, sometimes up to 9 months, glowing patiently in the dark. Then they pupate, hanging from their threads in a vulnerable stage that lasts a few days. Finally, they emerge as adults, delicate, mosquito-like insects with one purpose: to mate. Adult glowworms don't have functioning mouths or digestive systems. They live only a few days, just long enough to reproduce. Then they die. The larvae are surprisingly sensitive to disturbance. Loud noises, bright lights, or changes in temperature can stress them, causing their glow to dim or even go out. This is why visitors to glowworm caves are asked to remain quiet and keep their lights off. The silence, the darkness, and the soft blue glow combine to create an atmosphere of reverence, as if stepping into a sacred space. Similar glowing caves can be found in other parts of the world, from Australia to parts of Asia. Each population has adapted to its specific cave environment, but the strategy is the same: glow to attract, ensnare to survive. It's a quiet form of predation, passive yet effective, and it turns these dark caverns into living galleries of light. Deserts can bloom all at once. For most of the year, deserts appear barren, endless expanses of sand, rock, and dry shrubs under an unforgiving sun. The landscape seems lifeless, hostile, a place where water is scarce and survival is a constant struggle. But when the rains finally come, after months or even years of drought, the desert transforms overnight into something extraordinary. Seeds that have waited patiently in the soil, sometimes for decades, suddenly sprout. Within days, the landscape erupts in color. Wildflowers in purples, yellows, reds, and whites blanket the ground as far as the eye can see. This phenomenon, called a superbloom, turns the desert into a garden, a brief explosion of life that defies everything we expect from such a harsh environment. This mass flowering depends on precise conditions: enough rain at the right time, the right temperature, and seeds that are still viable. Desert plants have evolved remarkable strategies for survival. Their seeds are coated in chemicals that inhibit germination, washed away only by sufficient rainfall. This prevents them from sprouting during light, insufficient rains that wouldn't provide enough moisture for them to complete their life cycle. The bloom doesn't last long, sometimes just a few weeks. The flowers rush to grow, bloom, attract pollinators, and set seed before the water disappears and the heat returns. Time is of the essence. Bees, butterflies, and birds arrive in waves, drawn by the sudden abundance. They pollinate frantically, gathering nectar and pollen, helping the flowers reproduce. Desert animals that have been surviving on minimal resources suddenly have plenty. Then, as quickly as it began, the color fades. The flowers wither. Seeds drop to the ground. The desert returns to its familiar stillness, and the seeds settle back into the soil to wait again, patient and dormant, for the next rain that might not come for years. It's a reminder that even the driest, harshest places hold life. Not constant, but patient, waiting for the right moment to emerge. The desert is not dead. It's sleeping, and when conditions are right, it awakens in a riot of color and life that rivals any garden on Earth. Superblooms have become tourist attractions in places like California's Anza Borrego Desert and the Atacama Desert in Chile. When word spreads that a superbloom is happening, thousands of people flock to witness it, walking among carpets of flowers that won't be seen again for years. It's a fleeting spectacle, a brief moment when the desert reveals its secret vitality. Trees can share nutrients with their competitors. In a forest, trees of different species might seem to be in competition, each one fighting for sunlight, water, and space in the canopy. The tallest trees get the most light. The strongest roots claim the most nutrients. It seems like a battleground, where only the fittest survive and the weak are left behind. But beneath the surface, something more cooperative is happening, something that challenges our understanding of competition and survival. Through the mycorrhizal network, a vast web of fungal threads called hyphae connecting tree roots, trees can transfer nutrients to one another. This network, sometimes called the Wood Wide Web, is like an underground internet, allowing trees to communicate and share resources across the forest floor. A Douglas fir might send carbon to a nearby birch tree. A mother tree, large and mature, might support its seedlings through the network, even if those seedlings are shaded and struggling to photosynthesize on their own. Studies have shown that trees even share resources with different species, not just their own offspring. A dying tree may pass its remaining sugars to its neighbors, regardless of species, giving them a boost. In autumn, deciduous trees that lose their leaves and stop photosynthesizing may receive support from evergreens that continue producing energy through winter. The exchange flows both ways, with trees helping each other through seasons of plenty and scarcity. This underground network acts like a communal resource pool, a biological stock exchange where nutrients are traded based on need rather than competition. The fungi benefit too, receiving sugars from the trees in exchange for minerals and water they gather from the soil. It's a mutualistic relationship that's been evolving for hundreds of millions of years, since the first plants colonized land. Recent research has even suggested that trees can send warning signals through this network. If one tree is attacked by insects, it may release chemical signals into the mycorrhizal network, warning neighboring trees to boost their defensive compounds. The warned trees then produce more bitter or toxic chemicals in their leaves, making themselves less appetizing to herbivores. It's a form of communication that operates entirely underground, invisible to us but vital to the forest's survival. The forest, then, is not just a collection of individuals competing for resources. It's a community, interconnected and cooperative. Trees help each other, support each other, and communicate through an ancient network that predates human civilization. This changes how we think about forests, not as battlegrounds, but as societies, complex and collaborative, where the health of one is tied to the health of all. The atmosphere has layers we never see. When you look up at the sky, you're seeing only the lowest layer of Earth's atmosphere, the troposphere, where weather happens, where planes fly, where clouds form and birds soar. This is the layer we live in, the thin shell of air that supports all terrestrial life. But above that, invisible and often forgotten, stretch several more layers, each with its own unique properties and phenomena. Just above the troposphere is the stratosphere, extending from about 7 to 31 miles above Earth's surface. This is where the ozone layer resides, a concentration of ozone molecules that absorb the sun's harmful ultraviolet radiation. Without this protective layer, life on Earth's surface would be nearly impossible. The UV radiation would damage DNA, kill plants, and cause widespread cancers in animals. The ozone layer is why we can exist under open sky. Higher still is the mesosphere, stretching from about 31 to 53 miles up. This is where meteors burn up, creating the shooting stars we see on clear nights. The air is thin here, but still dense enough to create friction with incoming space debris, heating them to thousands of degrees and vaporizing them before they reach the surface. Every day, Earth is bombarded by tons of space dust and small rocks. But the mesosphere protects us, turning potential threats into fleeting streaks of light. Above the mesosphere is the thermosphere, where temperatures can soar to thousands of degrees, though the air is so thin you wouldn't feel the heat. This is where the International Space Station orbits, where auroras dance in green and purple curtains, and where the atmosphere begins to merge with the vacuum of space. The auroras occur when charged particles from the sun collide with oxygen and nitrogen molecules, exciting them and causing them to emit light. Finally, the exosphere fades gradually into space with no clear boundary. Here, the few remaining air molecules can travel hundreds of miles before colliding with another molecule. This is the edge of Earth's atmosphere, where our planet's protective envelope finally gives way to the void. Each layer has different temperatures, pressures, and compositions. Some are calm, others are turbulent, with winds that reach thousands of miles per hour. The thermosphere experiences jet streams of plasma flowing along magnetic field lines. The stratosphere has stable layers with very little vertical mixing. Together, they form a protective blanket around the planet, shielding us from radiation, regulating temperature, and making life possible. You can't see them, but they're there, layers of air, stacked like invisible quilts, each playing its role in the delicate balance that keeps Earth habitable. When astronauts look back at Earth from space, they can sometimes see these layers as faint bands of different colors, a visual reminder of the atmosphere's structure. From down here, we see only blue sky. But above us stretches a complex, layered system that has been protecting life for billions of years. Coral reefs glow under UV light. During the day, coral reefs are already among the most colorful ecosystems on Earth, teeming with fish in every imaginable hue, anemones waving in the current, and corals themselves displaying reds, oranges, purples, and yellows. But shine a UV light on them at night, and they transform into something otherworldly, almost alien. The corals fluoresce, glowing in electric blues, greens, pinks, and oranges that seem to defy nature. This fluorescence comes from proteins in the coral's tissue that absorb ultraviolet light and re-emit it as visible light. The proteins act like tiny light converters, taking invisible UV radiation from the sun and transforming it into a rainbow of visible colors. Scientists believe these proteins may serve several purposes. They might protect the coral from sun damage, especially in shallow waters where UV radiation is intense. They might help with photosynthesis, distributing light to the symbiotic algae living inside the coral's tissue. Or they might even attract prey, luring small organisms toward the coral's tentacles. At night, divers with UV lights witness a secret layer of color, invisible under normal conditions. The reef becomes a living light show, psychedelic and surreal, as if the corals are whispering in a language made of color. Fish appear to glow as well, many species having fluorescent patterns invisible in daylight. The entire reef transforms into a nighttime dance of bioluminescence and fluorescence, a hidden world that only reveals itself under the right wavelength of light. This fluorescence isn't unique to corals. Many marine organisms fluoresce, from jellyfish to certain species of sharks. Some scorpions fluoresce under UV light, glowing blue-green in the desert night. Even some flowers and lichens have fluorescent properties. But coral reef fluorescence is particularly striking because of its diversity and intensity. Hundreds of species all glowing in different colors, creating a submarine aurora. It's a reminder that the world holds layers we rarely perceive, hidden dimensions of beauty, visible only when we look in a different way. The reef you see during the day is just one version of the reef. At night, under UV light, it reveals an entirely different face, one that's been there all along, but hidden from our limited perception. We move through a world richer and stranger than our senses typically reveal, and every now and then, with the right tools or conditions, we get a glimpse of that hidden richness. Certain rocks record Earth's magnetic field. When lava cools into rock, something remarkable happens at the microscopic level. Tiny magnetic minerals inside the molten rock, primarily magnetite and hematite, align themselves with Earth's magnetic field, like billions of microscopic compasses all pointing north. As the rock solidifies and cools below a certain temperature called the Curie point, this alignment becomes locked in place, creating a permanent record of the magnetic field's direction at that moment in time. By studying these rocks, particularly in bands of volcanic rock on the seafloor, scientists have discovered that Earth's magnetic field has flipped many times throughout history. North becomes south, south becomes north. The magnetic poles swap positions completely. These reversals happen irregularly, sometimes every few 100,000 years, sometimes millions of years apart. The last reversal occurred about 780,000 years ago, and we're arguably overdue for another one. The process of a reversal is not instantaneous. It can take thousands of years, during which the magnetic field weakens significantly and may even develop multiple poles temporarily. During these transition periods, the protection the magnetic field provides against solar radiation decreases, potentially affecting climate and increasing radiation exposure for life on Earth's surface. We're currently in the middle of what might be the early stages of a reversal. The field has been weakening by about 5% per decade in recent years, and the magnetic North Pole has been moving faster than usual, drifting from Canada toward Siberia. Some scientists believe a reversal may be beginning, though it's impossible to predict with certainty. When it happens, and it will happen eventually, compasses will point the wrong way, and auroras might appear at the equator instead of the poles. But the rocks remember. They hold the history of every flip, every shift, every wobble. By examining volcanic rocks of different ages, scientists can reconstruct the history of Earth's magnetic field going back billions of years. The seafloor is particularly useful for this, because new crust is constantly forming at mid-ocean ridges, creating a magnetic tape recorder of field reversals spreading out from the ridge in both directions. This magnetic record also helped prove the theory of plate tectonics. When scientists mapped the magnetic patterns on the seafloor, they found symmetric stripes of normal and reversed magnetic fields on either side of mid-ocean ridges, strong evidence that the seafloor was spreading and continents were moving. The Earth's invisible shield, recorded in stone waiting to be read. It's a reminder that rocks are not just inert matter. They're historians, recording the planet's biography in patterns of magnetism frozen in time. The deepest hole ever dug is still shallow. In the 1970s and 82nds, Soviet scientists undertook an ambitious project to drill as far into the Earth as possible. The site was the Kola Peninsula in northwestern Russia, a remote and frozen landscape where they began drilling in 1970. The project continued for over 2 decades, and by 1989, they had reached a depth of about 7.5 miles, the deepest humans have ever penetrated into the planet. That sounds impressive, a testament to human engineering and persistence. But compared to the Earth's radius of nearly 4,000 miles, it's barely a scratch on the surface. If the Earth were an apple, the Kola super-deep borehole wouldn't even break through the skin. We've sent probes to other planets, we've split atoms, we've mapped the human genome, but we've barely scratched the surface of our own planet. The interior of Earth remains largely mysterious, known mostly through indirect methods like seismic waves. What they found during the drilling surprised scientists and changed some assumptions about the deep crust. The temperature was higher than expected, reaching about 180 degrees Celsius at the bottom, much hotter than predicted by models. This extreme heat made drilling increasingly difficult. Water existed far deeper than thought possible, flowing through fractured rocks at depths where scientists expected solid, impermeable layers. And the rocks at those depths were fractured and saturated, defying predictions that they would be solid and compressed by the immense pressure. The drill also encountered rocks that were much older than expected, including 2-billion-year-old formations. They found microscopic fossils of ancient plankton at depths of nearly 4 miles. They discovered that the structure of the crust was more complex than the simple layered model geologists had envisioned. The project was eventually abandoned, not because they ran out of curiosity or funding, but because the conditions became impossible. The heat and pressure made the drill bit behave more like a flexible rope than a rigid tool. The hole began to deviate from vertical. Equipment failed repeatedly. After spending the equivalent of hundreds of millions of dollars and drilling for 19 years, they could go no farther. The hole was sealed, and it remains. A tiny puncture in the planet's surface, a reminder of how little we truly know about what lies beneath our feet. The deepest humans have dug is less than 0.2% of the distance to Earth's center. We've barely begun to explore the planet we live on. The deep Earth remains alien territory, as inaccessible and mysterious as the surface of distant planets. Waves can travel across entire oceans. When an earthquake occurs beneath the sea, when tectonic plates suddenly shift and displace massive amounts of water, ripples spread outward in all directions. These are tsunami waves, and they travel thousands of miles across open ocean at incredible speeds, sometimes over 500 miles per hour, as fast as a jet airplane. In deep water, these waves are barely noticeable, often just a few feet tall, easily missed by ships passing overhead. The wave's energy is distributed across miles of deep ocean, making it almost invisible. It's only when these waves approach shallow coastal waters that they reveal their true power. As the ocean floor rises toward the shore, the tsunami slows down but piles up, concentrating all that energy into a much smaller space. The wave grows taller, steeper, sometimes reaching heights of 100 feet or more. What was nearly invisible in the open ocean becomes a devastating wall of water that can sweep inland for miles, destroying everything in its path. But tsunamis aren't the only waves that travel far. Ordinary ocean swells, generated by storms in one part of the world, can travel for thousands of miles before gently lapping onto a distant shore. Surfers in California might ride waves born from storms near New Zealand or Antarctica. The waves you see breaking on a beach might have traveled across an entire ocean, carrying energy from a storm that occurred days or even weeks ago. Waves are travelers, messengers carrying energy across the globe. They connect distant shores in ways we rarely consider. The same water that touches the coast of Japan also touches Hawaii, California, and Chile, all linked by waves that never stop moving, circling the ocean basins in endless patterns. The ocean itself is one continuous body of water, despite the names we give to different parts: Pacific, Atlantic, Indian. What happens on one side can echo across the entire globe, carried by waves that never stop moving. A storm in the Southern Ocean sends waves to Alaska. An earthquake off Japan creates tsunami warnings in Chile. The ocean is connected, and waves are the threads that bind it together, carrying energy and information across thousands of miles of open water. Scientists study wave patterns to understand ocean dynamics, predict weather, and track the movement of storms. Surfers study wave forecasts to find the best swells. Sailors learn to read waves to navigate safely. And all of us, whether we live by the coast or far inland, are connected to the ocean's rhythms through these traveling waves, these messengers of energy that link every shore. The soil beneath your feet is mostly empty space. Soil might feel solid under your feet, compact and stable, but it's actually more empty than full. Healthy soil is about 50% pore space, tiny gaps between particles where air and water flow, creating a hidden network of channels and chambers. The rest is a mix of minerals weathered from rock, organic matter from decomposed plants and animals, and living organisms ranging from bacteria to earthworms. These pores are essential to soil's function and to life itself. They allow plant roots to breathe, drawing in oxygen needed for respiration. Without these air spaces, roots would suffocate, unable to extract energy from the nutrients they absorb. The pores also allow water to drain through the soil rather than pooling on the surface, preventing waterlogging and erosion. At the same time, some pores are small enough to hold water against gravity through capillary action, storing it for plants to use during dry periods. Microbes move through these pores, exploring the soil, finding food, and interacting with roots. Water films coat the surfaces of soil particles, creating microhabitats where bacteria and fungi thrive. Gases diffuse through the pore spaces, exchanging carbon dioxide produced by roots and organisms for fresh oxygen from the atmosphere. The soil breathes, in a sense, inhaling and exhaling gases through this hidden network. When you dig into rich garden soil or forest floor, it feels light and crumbly, easy to work with. That's because it's full of air, alive with organisms, and structured by organic matter. This is ideal soil, balanced between solid and space. But soil can become compacted through heavy machinery, foot traffic, or loss of organic matter. When this happens, the pores collapse. The soil becomes dense, impermeable, and lifeless. Plants struggle to root. Water pools or runs off. The ecosystem collapses. The ground beneath you isn't solid. It's a sponge, breathing slowly, holding life in the gaps between particles. Every handful of soil is a miniature world, as complex as any ecosystem above ground, functioning through the interplay of solid, liquid, and gas, all held in delicate balance. This pore space also affects soil temperature. Air is a poor conductor of heat, so porous soil insulates better than compacted soil, protecting plant roots from temperature extremes. In winter, this insulation helps prevent freezing. In summer, it keeps roots cool. The soil's physical structure, then, is as important as its chemical composition, and that structure depends on the empty spaces as much as the solid particles. Some lakes explode. Most lakes are peaceful, serene places where water sits calm and still, perhaps rippled by breeze or disturbed by a fish breaking the surface. But in rare cases, lakes can become deadly time bombs, accumulating invisible danger in their depths. Certain volcanic lakes accumulate carbon dioxide deep underwater, leaking up from magma chambers below. The CO2 dissolves into the water under pressure, saturating the deep layers in a process that can continue for years or centuries. If something disturbs the lake, a landslide, an earthquake, a sudden temperature change, or even just the right shift in water circulation, the dissolved gas can suddenly escape. The CO2, no longer held under pressure, comes out of solution rapidly, like opening a shaken soda bottle, but on a massive scale. The lake erupts, not with water, but with an invisible cloud of carbon dioxide that rolls down into nearby valleys. This happened tragically in 1986 at Lake Nyos in Cameroon. A massive cloud of CO2 burst from the lake and flowed down into valleys and villages below, suffocating over 1,700 people and thousands of animals in their sleep. It was silent, odorless, and swift. Carbon dioxide is heavier than air, so it settled in low-lying areas, displacing oxygen. People went to sleep and simply never woke up. Survivors reported a strange smell, like rotten eggs or gunpowder, and then sudden loss of consciousness. The disaster shocked the world and sparked scientific investigation into how such lakes form and how to prevent future catastrophes. Researchers discovered that Lake Nyos sits in a volcanic crater, with CO2 leaking from magma below continuously. Over time, the gas had accumulated in the lake's depths, held under pressure by the weight of water above. Something, probably a landslide or sudden turnover of water layers, triggered the release. Today, pipes have been installed in Lake Nyos to slowly release the gas in a controlled manner, like a permanent fountain in the middle of the lake. The pipes reach down to the CO2-saturated depths, and natural pressure difference causes the water to flow up and out, releasing gas safely into the atmosphere. The fountain runs continuously, degassing the lake slowly to prevent another disaster. But other lakes around the world still hold this hidden danger, quietly accumulating pressure, including Lake Kivu on the border between Rwanda and the Democratic Republic of Congo. Lake Kivu is much larger than Nyos and contains not just CO2 but also large amounts of methane, making it potentially even more dangerous. Millions of people live on its shores. Scientists monitor it carefully, but the risk remains. These lakes are reminders that Earth's geological processes can create dangers we barely understand, hidden beneath seemingly peaceful waters. The ground can sing after rain, in deserts and dry plains, in places where water is scarce and plants struggle to survive. There's a smell that rises after the first rain. Earthy, rich, and almost intoxicating, like the breath of the earth itself. That scent has a name, petrichor, from the Greek words petra meaning stone and ichor, meaning the fluid that flows through the veins of gods. It comes from oils released by plants during dry periods. These oils accumulate on rocks, in soil, on leaves, anywhere moisture is scarce. They serve various purposes. Some inhibit seed germination until sufficient rain arrives, ensuring plants don't waste energy sprouting during brief, insufficient showers. Others may have antimicrobial properties, protecting plants in the harsh dry conditions. When rain finally arrives, these oils are released into the air, creating part of that distinctive scent. Mixed with the plant oils is a compound called geosmin, produced by soil bacteria called Actinomycetes. Geosmin literally means earth smell, and it's responsible for much of the earthy, musky quality of petrichor. When rain disturbs dry soil, it releases geosmin into the air. The bacteria produce this compound as a byproduct of their metabolism, and it accumulates in dry soil, waiting. When rain hits the ground, tiny droplets splash up, carrying these chemicals with them into the air. The splash creates aerosols, microscopic droplets suspended in the atmosphere, which spread the scent widely. This is why the smell of rain can arrive before you see or feel the drops themselves. The aerosols travel on the wind, announcing the rain's arrival. Humans are extremely sensitive to geosmin. We can detect it at concentrations as low as 5 parts per trillion. That's incredibly dilute, yet our noses pick it up immediately. Some scientists believe this sensitivity evolved because rain often meant the arrival of water and food in our ancestors' environments. The smell of petrichor signaled that dry stream beds would flow again, that plants would green and fruit, that hunting and gathering would be easier. Our brains learn to associate this smell with survival. Interestingly, camels and some other desert animals are also highly sensitive to geosmin, possibly using it to detect distant oases or approaching rainstorms. The scent of rain on dry earth is more than just pleasant. It's information, a chemical message that carries meaning for many creatures. So when you smell rain on dry earth, you're inhaling a chemical signal millions of years old, a scent that whispers, water has returned. It's a message from the soil, from the plants, from bacteria that have been waiting patiently for this moment. And your brain, carrying instincts from ancient ancestors, understands what it means and finds comfort in the smell. Some rocks float. Pumice is a paradox, a rock so light it can float on water, defying one of the most basic assumptions we have about stones. It forms when lava, filled with gas bubbles, erupts violently from a volcano and cools rapidly. The gas, mostly water vapor and carbon dioxide, becomes trapped in the solidifying lava, creating a rock that's more air than stone, riddled with tiny holes like a frozen foam. When you hold pumice, it feels impossibly light, sometimes lighter than water itself. Its surface is rough and abrasive, useful for smoothing skin or polishing surfaces, but its most remarkable property is its buoyancy. After volcanic eruptions, particularly those involving explosive interactions with water, massive rafts of pumice can float across the ocean for years, sometimes covering hundreds of square miles of sea surface. These floating pumice rafts travel thousands of miles on ocean currents, journeying across entire ocean basins before finally becoming waterlogged and sinking. During their journey, they provide new habitats for marine life. Barnacles and other organisms attached to the floating rocks. Fish shelter beneath them. Marine plants drift with them. The rafts become floating islands of life, carrying organisms to distant shores they would never reach otherwise. This has important ecological implications. After disasters like coral bleaching events or destructive storms, Pumice rafts can help repopulate damaged reefs by carrying coral larvae, algae, and other organisms across vast distances. They're like nature's lifeboats, spreading life across the oceans, connecting isolated islands and coastlines through unexpected migrations. Eventually, usually after weeks or months, the pumice becomes waterlogged. Water seeps into the tiny pores, gradually filling the air spaces. The rock becomes heavier, denser, until finally it loses its buoyancy and sinks to the ocean floor, taking its passengers with it. But for a time, sometimes a long time, it defies expectations. A rock that drifts and floats, light as a sponge, carried by currents, connecting distant lands with unexpected passengers. Pumice has been used by humans for thousands of years, valued for its abrasive properties. Ancient Romans used it in concrete. Modern industries use it for polishing, horticulture, and even in toothpaste. But its most remarkable use is natural. Nature's ferry service, spreading life across oceans, one floating rock at a time. The Earth's core is as hot as the sun's surface. Deep below your feet, nearly 4,000 miles down through rock and magma, lies the Earth's core, a sphere of solid iron surrounded by liquid metal. The temperatures there are almost inconceivable, reaching about 10,000 degrees Fahrenheit, or around 5,700 degrees Celsius. That's roughly the same as the surface of the sun, though the core's density and pressure are far greater. This incredible heat comes from two main sources. First, there's primordial heat, leftover energy from Earth's formation billions of years ago. When the planet was forming, countless collisions between protoplanetary material generated enormous amounts of heat. Much of that energy is still slowly radiating outward, trapped by thousands of miles of insulating rock. Second, there's radioactive decay. Elements like uranium, thorium, and potassium in the Earth's interior break down over time, releasing energy in the form of heat. This process has been ongoing for billions of years and will continue for billions more. The core remains molten, or at least the outer core does, because it's insulated by the immense thickness of the mantle and crust above it. Heat escapes incredibly slowly, taking millions of years to travel from the core to the surface. The inner core, despite being even hotter, is solid because the pressure there is so immense, millions of times atmospheric pressure at Earth's surface, that iron cannot exist in liquid form. This hidden furnace drives many of Earth's processes. The heat causes convection in the mantle, the slow churning movement of semi-solid rock that drives plate tectonics. Plates collide, forming mountains. They pull apart, creating ocean basins. They slide past each other, causing earthquakes. All of this movement, all this geological activity, is powered by heat from the core. The core also generates Earth's magnetic field through a process called the geodynamo. The liquid outer core, made mostly of molten iron and nickel, flows in complex patterns as the Earth rotates. These moving electric conductors create magnetic fields, and the interaction of these fields generates the planet's overall magnetic field. This magnetic shield protects us from harmful solar radiation and cosmic rays, deflecting charged particles that would otherwise strip away the atmosphere and bombard the surface. Without the core's heat, Earth would be geologically dead, like Mars or the Moon. There would be no volcanoes, no earthquakes, no moving continents. The magnetic field would fade, leaving the planet vulnerable to solar wind. The atmosphere might slowly erode into space. Life, if it could exist at all, would be very different. So while the core will never be seen or touched, impossibly deep and impossibly hot, it shapes everything above it. The mountains, the oceans, the very atmosphere we breathe. A hidden furnace, burning in darkness, keeping the world alive. Clouds are heavier than you think, but lighter than they seem. We've touched on the weight of clouds before, but let's dwell here a moment longer because the contradiction is so profound. A single cumulus cloud, the puffy white kind you see on a pleasant afternoon, can contain over 500,000 pounds of water. That's the weight of about 100 elephants or 40 cars, suspended thousands of feet above your head, drifting lazily across the sky. Storm clouds are even heavier. A single thunderstorm cell might contain millions of pounds of water, tens of millions of gallons, all hanging in the air, dark and threatening. When you see a massive thunderhead tower into the sky, you're looking at more water than fills many small lakes, somehow defying gravity, held aloft by nothing but air. Yet they float. And here's why. The water is divided into billions upon billions of tiny droplets, each so small that air resistance keeps it suspended. A typical cloud droplet is about 10 to 20 micrometers in diameter, much smaller than the width of a human hair. At this scale, air is more like a thick fluid than an empty space. The droplets drift on currents, swirl in eddies, and are held up by updrafts, columns of rising warm air that push upward against gravity. As long as the updraft is strong enough, the droplets stay suspended. They're constantly moving, colliding, merging, and splitting. When droplets collide and merge, they grow larger through a process called coalescence. Eventually, some droplets become large enough that they can no longer be supported by updrafts. They overcome air resistance and begin to fall. Other droplets collide with them as they fall, making them grow even larger, and finally they emerge from the cloud base as rain. Inside a thunderstorm, the updrafts can be incredibly powerful, strong enough to support even large hailstones. Hail forms when raindrops are carried upward by updrafts into the freezing layers of the cloud, where they freeze. They fall, gathering more water, then get carried up again, adding another layer of ice. This can happen multiple times, creating hailstones with concentric layers like an onion. The largest hailstones, some as large as softballs, require sustained updrafts of over 100 miles per hour to stay aloft long enough to grow. Clouds are also constantly forming and dissipating. The cloud you see one moment isn't exactly the same cloud a minute later. Water molecules are constantly condensing from invisible vapor when air cools and evaporating back into vapor when air warms. A cloud is less like a solid object and more like a process, a temporary visible manifestation of atmospheric conditions. It's a sculpture made of mist, constantly reshaping itself, born from invisible vapor and returning to invisibility when conditions change. From an airplane cruising above the clouds, they look solid enough to walk on, like vast white plains or mountain ranges stretching to the horizon. But step out onto one, and you'd fall right through, surrounded by nothing but cold, damp fog. Clouds are illusions in a sense, solid from a distance but insubstantial up close. They hold oceans in the sky, heavy and light at once, caught between earth and space, in an eternal dance of condensation and evaporation, visible proof of water's endless cycle through the atmosphere. Some mountains are hollow. Mountains appear solid, immense masses of rock thrusting skyward, monuments to the Earth's geological forces. But some mountains are riddled with emptiness, laced with caves that extend for hundreds of miles beneath the surface, creating vast hollow spaces that few people will ever see. The longest known cave system, Mammoth Cave in Kentucky, has over 400 miles of mapped passages, and explorers discover new sections every year. The cave formed over millions of years as water seeped through cracks in limestone, slowly dissolving the rock. Carbon dioxide in the water forms carbonic acid, which eats away at limestone, gradually creating spaces. What begins as tiny cracks become tunnels. Tunnels merge and expand into chambers. Over geological timescales, entire underground river systems develop. These caves contain massive chambers, some large enough to hold a cathedral. Stalactites hang from ceilings like frozen waterfalls, formed drip by drip over thousands of years as mineral-rich water deposits tiny amounts of calcite, Stalagmites rise from floors to meet them. Sometimes they join, creating columns that span from floor to ceiling. The formations are delicate, beautiful, and incredibly fragile, easily damaged by a careless touch. Underground rivers flow through many cave systems, carving ever deeper into the rock. During floods, these rivers can fill passages completely, creating dangerous conditions for explorers. In dry seasons, the rivers shrink to trickling streams, revealing passages that are usually submerged. Inside these mountains, darkness is absolute. Not the darkness of a moonless night, but total absence of light. Cave-adapted species have evolved here, creatures that have never seen daylight. They're often blind, having lost their eyes over generations of evolution, with no selective pressure to maintain them. Many are colorless, pale, or translucent, since pigments serve no purpose in perpetual darkness. Blind cave fish navigate by sensing water pressure and movement. Cave beetles have elongated antennae to feel their way. Cave spiders spin webs in the dark, catching flying insects that venture into the cave entrances. The temperature in deep caves stays constant year-round, typically matching the average annual temperature of the region above. In Kentucky, Mammoth Cave stays around 54 degrees Fahrenheit year-round. This stability makes caves valuable for preserving food, historical artifacts, and even data storage. During wars, some caves have been used as shelters or storage for precious materials. The mountain appears solid from outside, an immense block of stone. But within, it's laced with emptiness. An inverted landscape where rivers flow upside down, where stone drips like water, and where life has adapted to eternal night. It's a hidden world, as alien as anything beneath the ocean, right beneath our feet, waiting in the dark. The atmosphere glows at night. If you could see in the right wavelengths, or if you were sensitive to very faint light, you'd notice that the night sky glows softly, even when there's no moon, no stars visible, no city lights. This phenomenon is called airglow, a faint emission of light from the upper atmosphere caused by chemical reactions happening 50 to 300 miles above Earth's surface. During the day, solar radiation, ultraviolet and X-rays from the sun, energizes oxygen and nitrogen molecules in the upper atmosphere. These molecules absorb the energy, becoming excited. At night, they release that stored energy as light, mostly in the green part of the spectrum, though red and other colors occur as well. It's not the same as auroras, which are caused by solar particles colliding with the atmosphere near the poles. Airglow is a constant, gentle emission, happening every night, all around the world, at all latitudes. Astronauts aboard the International Space Station can see airglow clearly, a faint green layer hovering above Earth's surface, like a halo or a soft glow outlining the curve of the planet. It's quite beautiful in photographs from space, a thin luminous band separating the dark Earth from the black void of space. From the ground, it's usually too dim to notice without sensitive equipment, but it's there, contributing to the brightness of the night sky, even in the absence of other light sources. The study of airglow helps scientists understand the chemistry and dynamics of the upper atmosphere. The intensity and color of airglow can reveal information about atmospheric composition, temperature, and the effects of solar radiation. Variations in airglow can indicate atmospheric waves, disturbances that propagate through the upper atmosphere like ripples on a pond. It's a reminder that even darkness radiates light, that the atmosphere is never truly still or inert. Chemical reactions continue, energy is exchanged, and the sky glows softly with the aftermath of sunlight, a gentle luminescence that speaks of ongoing processes we rarely see or consider. The night is not as dark as it seems. It has its own light, quiet and persistent, a glow that connects the surface to space. Your shadow is always different. Every shadow you cast is unique, an ephemeral artwork that will never be exactly replicated. Shadows depend on the position of the sun, which changes continuously throughout the day and year. At noon in summer, when the sun is high, your shadow is short and sharp, a dark pool at your feet. At sunrise or sunset, your shadow stretches long and soft, sometimes extending hundreds of feet, distorted and dramatic. The time of year matters too. In winter, when the sun's arc across the sky is lower, shadows are longer even at noon. In summer, the sun climbs higher and midday shadows shrink. Your latitude also plays a role. Near the equator, shadows change more dramatically throughout the year, while closer to the poles, the sun's path is more extreme, creating months of endless shadow or no shadow at all. Atmospheric conditions affect shadows as well. Humidity, dust, and pollution scatter light, creating softer, more diffuse shadows. On a clear, dry day, shadows are crisp and dark, with sharp edges. On a cloudy day, shadows nearly disappear, softened into gentle gradients because the cloud layer diffuses sunlight, making it come from many directions at once rather than a single point source. Even the surface your shadow falls on changes its appearance. A shadow on grass looks different from one on concrete or sand. Texture, color, and reflectivity all influence how the shadow appears. A shadow cast on water ripples and dances. A shadow on snow seems darker by contrast. You've cast thousands, perhaps millions of shadows in your life, and no two were exactly the same. Each one was a moment, a position in space and time, recorded briefly in darkness and then gone, replaced by the next. Shadows are ephemeral, personal, and endlessly fleeting. A reminder that even something as simple as darkness is never truly the same twice. Ancient sundials relied on this predictability of shadows to tell time, using the shadow cast by a vertical rod to mark the hours. Different civilizations developed sophisticated understanding of shadow patterns, using them for navigation, architecture, and timekeeping. Even today, the study of shadows, how they fall, how they change, reveals information about time, position, and the geometry of light. The wind has a memory. Wind is more than just moving air. It's a traveler, a messenger carrying traces of everywhere it's been. When scientists sample the air, analyzing the particles suspended in it, they can trace them back to their origins, sometimes thousands of miles away. The wind has a memory, written in dust and pollen, in salt spray and smoke, in molecules and microbes that drift on its currents. Dust from the Sahara Desert crosses the Atlantic Ocean, blown by trade winds, and falls on the Amazon rainforest, fertilizing the soil with nutrients. The Amazon depends on this African dust, which contains phosphorus and other minerals that the rainforest's nutrient-poor soils lack. Every year, millions of tons of Saharan dust make this journey. A transcontinental delivery service, operating on geological timescales, ash from volcanic eruptions, can circle the globe, suspended in the stratosphere for months or years. The 1991 eruption of Mount Pinatubo in the Philippines injected so much ash and sulfur dioxide into the atmosphere that it affected global temperatures for years, cooling the planet slightly by blocking a fraction of sunlight. Sunsets became more vivid, painted red and orange by the ash scattering light. Pollen drifts on the breeze, sometimes traveling hundreds of miles from its source. During spring, winds carry pollen from forests and fields, coating everything with a fine yellow dust that makes cars look dirty and triggers allergies. But it's also pollinating flowers far from the parent plant, spreading genetic diversity across vast distances. Even smoke from wildfires travels thousands of miles. Smoke from fires in the western United States has reached the East Coast, hazing the sky and creating apocalyptic sunsets. Smoke from Siberian fires has been detected in Alaska and Canada. The wind carries the evidence of these fires, the scent and particles of combustion, announcing distant disasters to places that might never see the flames. Microorganisms travel on the wind too. Bacteria, fungal spores, viruses, all suspended in the air and transported across continents. This aerial microbial community is called the aerobiome, and it's only recently being studied in detail. Every breath you take might contain microbes from a distant forest or desert, invisible hitchhikers on the wind's journey. So when you feel the wind on your face, remember, it's been places. It carries stories written in particles, invisible but real. When you breathe in, you're inhaling molecules that have traveled across continents, carrying traces of distant places. A desert, a sea, a forest you'll never visit, but which has, in a tiny way, visited you. The wind connects us all, blending the atmosphere into one shared reservoir, constantly mixing, constantly traveling, never still. Silence doesn't exist on Earth. True silence, the absolute absence of sound, is almost impossible to find on Earth. Even in the quietest natural places, there's always something. The rustle of leaves in a gentle breeze, the distant call of a bird, the hum of insects, the barely audible sound of your own heartbeat and breath, the whisper of wind, the trickle of water far away. The quietest place on Earth is not natural but artificial, an anechoic chamber at Orfield Laboratories in Minnesota. This room is designed to absorb 99.99% of sound, with walls covered in sound-absorbing foam wedges and floating construction that isolates it from external vibrations. Inside, the sound level can drop to -9 decibels, quieter than anything found in nature. People who enter this chamber report unsettling experiences. Without external sound, they become acutely aware of their own bodies. They hear their heartbeat, loud and insistent. They hear their lungs expanding and contracting. They hear the rush of blood through their veins, the clicking of joints, the gurgling of their digestive system. Some people hear ringing in their ears, tinnitus, that's normally masked by ambient sound. Most people can't stand the chamber for more than a few minutes. The absence of sound is disorienting, almost disturbing. Humans are accustomed to constant auditory input. We navigate partly by sound, using it to understand our environment. In absolute silence, that sensory input vanishes, and the brain struggles to process the absence. Outside these artificial spaces, Earth is never silent. Wind whispers through grass, waves crash on shores, ice creaks in glaciers, rocks shift minutely as temperature changes. Tectonic plates groan under immense pressure, creating sounds far below human hearing range. Life makes noise constantly. Birds call, insects chirp, frogs croak, leaves rustle. Even in remote wilderness, away from human activity, the soundscape is rich. At night in a forest, you might hear owls hunting, mice scurrying, bats echolocating, trees creaking as they cool. In the desert, wind sings over dunes, coyotes howl, insects buzz. The ocean is even noisier. Whales call, dolphins whistle, shrimp snap, waves break. The earth hums with life and activity, creating a symphony so familiar we often stop noticing it. But it's always there, a reminder that the world is alive, never fully still, always moving, breathing, sounding, even in the deepest night, even in the remotest wilderness. Silence, true silence, is not part of the natural world. It's an absence we can only create artificially, and when we do, we find it almost unbearable. The horizon is always moving. The horizon line, the distant edge where Earth appears to meet sky, seems fixed and constant, a stable reference point. But it's actually in constant flux, always shifting based on your position and the conditions around you. The horizon you see is unique to you, defined by your elevation, the curvature of the Earth, and even the density of the atmosphere. For someone standing at sea level, the horizon is about 3 miles away. That's where the curve of the Earth drops away enough that you can no longer see the surface. Climb to a higher elevation, and the horizon extends farther. From the top of a mountain, you might see 100 miles or more to the horizon. From an airplane at cruising altitude, the horizon can be hundreds of miles away, and you can actually see the curvature of the Earth as a subtle arc. The horizon's distance follows a mathematical relationship with your height above the surface. Roughly, the distance to the horizon in miles is about 1.22 times the square root of your elevation in feet. So from 6 feet above the ground, you can see about 3 miles. From 100 feet, about 12 miles. From 35,000 feet in an airplane, about 230 miles. But atmospheric conditions complicate this. Refraction, the bending of light as it passes through air of different densities, can make the horizon appear higher or lower than it geometrically should be. On some days, cold, dense air near the surface can create a mirage effect, making distant objects appear closer or allowing you to see beyond the geometric horizon. This is called a superior mirage, and it can make ships or islands appear to float above the horizon. Temperature inversions, where warm air sits atop cold air, can bend light downward, extending your line of sight beyond the normal horizon. In extreme cases, this can create a green flash at sunset, a brief moment when the upper edge of the sun appears green due to atmospheric refraction. The horizon you see at sea is different from one you see in the mountains or the desert. Over water, the horizon is sharp and defined. In mountains, terrain interrupts the view, creating multiple horizon lines at different distances. In a forest, the horizon disappears entirely, replaced by trees. The horizon is not a place you can reach. It retreats as you approach, always staying the same distance away. It's not a physical boundary, but a perspective, a limit to your vision imposed by the planet's curvature and the atmosphere. No one else sees exactly the same horizon line you do. It's personal, unique to your position, always changing as you move, forever out of reach. Ancient mariners used the horizon as a reference for navigation, measuring the angle of the sun or stars above it to determine latitude. The flat, level horizon at sea made it a reliable baseline. Even today, pilots and sailors refer to the horizon to orient themselves, using it as a visual level. When instruments fail, rivers older than mountains flow through them. Some rivers are ancient beyond imagination, older than the mountains they flow through. They've been carving their paths for tens of millions of years, long before the current landscape existed. As mountains rose through tectonic forces, these rivers cut down through the rock at nearly the same rate, maintaining their courses even as the land around them lifted thousands of feet. The Colorado River carved the Grand Canyon, but the river is older than the canyon itself. It was already flowing across relatively flat terrain when the Colorado Plateau began to rise. As the land lifted, the river cut downward, maintaining its course, slicing through layer after layer of rock. The result is a canyon, a mile deep in places, revealing 2 billion years of geological history in the exposed rock walls. Similar stories play out around the world. The Ganges predates the Himalayas, flowing across an ancient plain before the mountains rose. As India collided with Asia, the river adapted, cutting through the rising terrain. The Nile has maintained aspects of its course for millions of years, flowing north while the African continent shifted beneath it. These ancient rivers are called antecedent rivers. They're older than the mountains, older than the valleys, persistent through geological upheaval. While empires rose and fell, while species evolved and went extinct, these rivers continued flowing, patient and eternal, cutting deeper and deeper into rising land. When you stand at the edge of a canyon, you're not just seeing the power of water, You're witnessing a contest between two geological forces, the uplift of land and the erosion of rivers. In this case, the river won, maintaining its course while carving a monument to persistence and time. Snow can be red, green, or even watermelon-scented. In high alpine regions and polar areas, snow sometimes appears tinted with color, pink, red, or even greenish hues. This isn't pollution or reflection from minerals. It's alive. Tiny algae called snow algae or Chlamydomonas nivalis thrive in these extreme conditions, coloring the snow with their pigments. The most common is watermelon snow, which appears pink or red and, remarkably, sometimes smells faintly sweet, like watermelon. The algae contain red pigments called carotenoids that protect them from intense UV radiation at high altitudes. These pigments give the snow its color. When present in large numbers, the algae can turn entire snowfields pink, creating surreal landscapes that look like strawberry slushies covering mountainsides. Green snow is caused by different algae species that contain more chlorophyll. Yellow or brown tints can come from dust, pollen, or yet other microorganisms. Each color represents a different microscopic community thriving in conditions that seem impossibly harsh: freezing temperatures, intense radiation, and minimal nutrients. These algae are remarkably adapted to their environment. They can survive being frozen solid, entering a dormant state during winter and becoming active again when conditions improve. They photosynthesize using the faint light that penetrates the snow, producing energy from the sun just like plants, but in an icy environment. Colored snow has implications for climate. Darker snow absorbs more heat than pure white snow, potentially accelerating melting. As climate warms and snow algae become more abundant, they could contribute to feedback loops that increase melting rates, particularly in polar regions. What seems like a curiosity, pink snow, might be a small but significant factor in Earth's changing climate. So when you hear of watermelon snow, know that it's not just a quirk but an ecosystem, life adapting to the edge of habitability, finding a niche where few other organisms can survive, and in the process adding unexpected color to the frozen world. The oldest water on Earth is billions of years old. Deep in a mine in Ontario, Canada, scientists discovered water that has been isolated from Earth's surface for possibly 1 to 2 billion years. This ancient water, trapped in rock fissures more than a mile underground, is older than complex multicellular life. It's been sitting in darkness, undisturbed, since before animals existed, before plants colonized land, before oxygen-breathing life dominated the planet. The water is incredibly salty, much more so than seawater, with high concentrations of dissolved minerals. It tastes, according to one scientist who carefully sampled it, terrible, bitter, and metallic. But taste aside, it's chemically fascinating. The water contains gases like hydrogen and methane produced by reactions between water and rock. Radiolysis, where radioactive decay of elements in the rock breaks water molecules apart. These chemical reactions could support life. Indeed, scientists found bacteria living in this ancient water, organisms that have been isolated from the surface for potentially millions of years. They survive on chemical energy, not sunlight, much like life around deep-sea hydrothermal vents. This discovery has implications for understanding where life might exist elsewhere in the universe. On Mars, on moons like Europa or Enceladus, anywhere liquid water might exist beneath the surface. The concept of water being old is somewhat strange because water molecules themselves are constantly recycling. The water you drink today might contain molecules that were once in dinosaurs, in ancient oceans, in clouds over Egypt during the time of the pharaohs. Water is reused endlessly through Earth's hydrological cycle, but this deep water is different. It's been isolated, cut off from the cycle, preserved in rock like a time capsule. It's the same water that was there when it was first trapped, unchanged by eons of surface processes. When scientists pump it out and study it, they're touching a piece of Earth's deep past, liquid history preserved in darkness. Other ancient water exists in deep aquifers, trapped in porous rock layers for millions of years. Some groundwater in the Sahara is thousands of years old, left over from when the region was much wetter. This fossil water is being pumped out faster than it's replenished, essentially mining an ancient resource that won't be replaced on human timescales. Some trees produce chemicals that protect their neighbors. When a tree is attacked by insects or disease, it doesn't suffer in silence. Many trees produce defensive chemicals, bitter compounds, toxins, or sticky resins that make them less appealing to herbivores. But remarkably, they also warn their neighbors. Trees release volatile organic compounds into the air, chemical signals that drift on the breeze to nearby trees. When neighboring trees detect these warning signals, they respond by boosting their own defenses, even though they haven't been attacked yet. They increase production of tannins, phenols, or other protective compounds, making their leaves more bitter or toxic. This preemptive defense can significantly reduce the damage from subsequent attacks. Acacia trees in Africa do this when giraffes browse on their leaves. As the giraffe moves from tree to tree, upwind trees receive the chemical warning and become less palatable, sometimes forcing the giraffe to move hundreds of meters away to find trees that haven't received the signal. Willows and birches show similar behavior. When caterpillars attack one tree, nearby trees of the same, and even different species increase their defensive chemistry. The signals can be specific too. Different threats elicit different chemical warnings, allowing neighbors to tailor their responses. This isn't altruism necessarily. Many of the warned trees are genetic relatives, offspring or clones of the signaling tree. There's evolutionary advantage in protecting your kin. But even unrelated trees benefit from this system, creating networks of mutual protection that help the entire forest resist herbivore outbreaks. The chemical language of plants is complex and still being decoded. They communicate not just warnings, but information about drought, nutrient availability, and even the presence of helpful fungi or bacteria. The forest floor is filled with invisible messages, a constant chatter of chemical signals that we're only beginning to understand. Plants were doing social networking millions of years before humans invented the term. The deepest ocean trench could fit Mount Everest with room to spare. The Mariana Trench in the Pacific Ocean is the deepest part of any ocean on Earth, plunging down nearly 36,000 feet at its lowest point, the Challenger Deep. To put that in perspective, if you placed Mount Everest, the world's tallest mountain at 29,000 feet, at the bottom of the trench, its peak would still be more than a mile underwater. The pressure at these depths is crushing, over 1,000 times atmospheric pressure at sea level, equivalent to having 50 jumbo jets stacked on top of you, yet life exists even here. In 2012, filmmaker James Cameron descended to the Challenger deep in a specially designed submersible and found life, small amphipods, flatworms, and microbial mats covering the sea floor. These creatures have adapted to the extreme conditions in remarkable ways. Their cell membranes are specially structured to remain flexible under immense pressure. They have no air spaces in their bodies. Air would compress to nothing at these depths. Their biochemistry operates efficiently in near-freezing temperatures and total darkness. The trench formed where the Pacific Plate is being subducted beneath the Mariana Plate, one tectonic plate sliding beneath another and plunging into the mantle. This process is ongoing, and the trench continues to be active. Earthquakes rumble through regularly. Volcanic vents release superheated water and gases from below. Only 4 descents to the bottom of the Challenger Deep have ever been made, far fewer than the number of people who've walked on the moon. The deep ocean remains one of Earth's least explored frontiers, more alien and less accessible than the surface of Mars in many ways. What's down there? We've barely glimpsed it. strange fish with translucent bodies and enormous mouths, jellyfish that pulse like ghosts, crustaceans and worms living on marine snow, the constant gentle fall of dead material from the sunlit surface far above. Some feed on chemicals from hydrothermal vents. Others wait in the dark for something, anything, to drift by. The trench is a reminder that Earth still holds vast unknowns, places where humans have barely ventured, ecosystems we don't fully understand. The deep ocean is not empty. It's full of life adapted to conditions we can barely imagine, thriving in the deepest, darkest, most pressurized environments on the planet. Stones can walk across the desert on their own. In Death Valley, California, rocks weighing hundreds of pounds leave long trails across the flat desert floor of Racetrack Playa. These rocks, some as large as a person, appear to move on their own, sliding across the dry lakebed and leaving grooves behind them. For decades, the phenomenon baffled scientists. No one had ever actually witnessed the rocks moving. Theories abounded: strong winds, magnetic fields, ice, even pranksters moving the rocks at night. But none fully explained the patterns. The trails were sometimes straight, sometimes curved, sometimes parallel, sometimes crossing. Some rocks moved while adjacent ones stayed still. The mystery deepened. Finally, in 2014, scientists using time-lapse cameras and GPS trackers captured the process. The mechanism requires a specific set of conditions, rare but not impossible. During winter, water collects on the playa. On cold nights, it freezes into a thin sheet of ice. As the sun rises and the ice begins to melt, it breaks into large floating panels. Light winds, as gentle as a breeze, push these ice sheets across the still liquid layer of water beneath. The rocks, frozen into the bottom of the ice, are pushed along with it. Because the ice is so thin and the water layer provides lubrication, even light winds can move heavy rocks. As the ice melts completely, it leaves behind only the rock and its trail, with no obvious explanation for how it got there. The sailing stones move slowly, just a few inches per minute, but over the course of hours they can travel hundreds of feet. The trails can last for years in the dry desert environment, preserving the evidence long after the ice has vanished. It's a perfect example of how nature can create seemingly impossible phenomena through the right combination of conditions. The rocks aren't defying physics, they're demonstrating it, in a dance of ice, water, wind, and stone that happens only rarely, in only a few places on Earth. There are places where two oceans meet, but don't mix. At certain locations around the world, you can see a visible boundary where two bodies of water meet, but don't immediately mix. The colors and textures are distinct. One side might be darker, the other lighter, creating a line that looks almost painted across the sea. This happens when waters with different densities, salinities, temperatures, or sediment loads meet. One famous example is where the Baltic Sea and the North Sea meet near Skagen, Denmark. The Baltic is less salty because it receives so much fresh water from rivers. The North Sea is saltier. Where they meet, there's a visible boundary. The waters do mix eventually, but not instantly, creating a temporary line visible from shore. Another example is where glacial meltwater rivers flow into the ocean, carrying fine sediment called glacial flour, rock ground to powder by glaciers. This sediment gives the water a milky, light blue color. When it meets the dark blue ocean water, there's a sharp color contrast that can persist for miles. These boundaries aren't permanent walls. Eventually, turbulence, currents, and time blend the waters together. But in the moment, they create striking visual lines, as if someone drew a border across the sea. They're reminders that the ocean isn't uniform, that water has properties, salinity, temperature, density, that create invisible structures within the sea, boundaries and layers that shape how water moves and mixes. Similar phenomena occur at river mouths where freshwater meets saltwater, called haloclines. The fresh water, being less dense, flows over the denser salt water, creating a two-layer system. Divers in these areas sometimes experience blurred vision at the boundary layer, where light refracts differently through the mixing waters. Lightning can strike the same place repeatedly. Contrary to popular belief, lightning does strike the same place twice. In fact, it strikes some places over and over again. Tall structures like the Empire State Building are hit dozens of times per year. The building acts as a lightning rod, its height making it a preferred path for electrical discharge from clouds to ground. Lightning seeks the path of least resistance to the ground, and tall pointed objects reduce the distance the strike must travel through air, which is a poor conductor. Once a location has been struck, the charred path through the air can actually make subsequent strikes slightly more likely in the immediate aftermath, as the ionized air conducts electricity better than surrounding air. Some places are struck by lightning far more than others due to local geography and weather patterns. The Congo Basin in Africa experiences more lightning than anywhere else on Earth. Lake Maracaibo in Venezuela has a phenomenon called the Catatumbo lightning, where storms produce lightning almost every night for up to 10 hours at a time, sometimes generating 280 strikes per hour. This occurs where cool mountain breezes meet warm, moist air over the lake, creating perfect conditions for electrical storms. Lightning is not a single bolt, but often multiple strokes following the same channel in rapid succession, too fast for the eye to distinguish. What looks like one flash might be 4 or 5 strokes, each one following the ionized path created by the previous one. The energy in a lightning bolt is immense but brief, about 1 billion joules delivered in a fraction of a second. The bolt heats the air to 50,000 degrees Fahrenheit, 5 times hotter than the sun's surface. This superheating causes the air to expand explosively, creating the thunder we hear. Because light travels faster than sound, we see the flash before we hear the boom. Lightning strikes somewhere on Earth about 100 times per second, or 8 million times per day. It's a constant, global phenomenon, the planet discharging electrical imbalances between clouds and ground, a reminder of the immense energies constantly at play in Earth's atmosphere. The Earth has a second moon. Sometimes, Earth doesn't always have just one moon. Occasionally, small asteroids are captured temporarily by Earth's gravity, becoming what are called quasi-satellites or mini-moons. These objects orbit Earth for months, or even years before escaping back into independent orbits around the Sun. These temporary moons are usually very small, ranging from a few feet to a few hundred feet in diameter, too small and distant to see without telescopes. One known quasi-satellite, called 2016-03, has been dancing around Earth for about a century and will likely continue for several more centuries. It never gets very close, staying at least 38 times farther away than our real moon, but it's gravitationally bound to Earth during this time. Another object, 2020 CD3, was captured and orbited Earth for a few years before being flung back out into space in 2020. Astronomers estimate that at any given time, Earth might have one or more of these mini-moons, though most go undetected because they're so small and dark. These temporary captures happen because Earth's gravitational influence extends far into space. Small objects passing nearby can be deflected into temporary orbits if the conditions are just right, the right speed, the right angle, the right distance. Eventually, gravitational perturbations from the Sun and Moon destabilize these orbits, and the objects escape. The discovery of minimoons is relatively recent because detecting them requires sensitive telescopes and automated survey systems scanning the sky for moving objects. As our detection technology improves, we're finding more of them, suggesting they're more common than once thought. So Earth's family of satellites is not fixed. Our moon is permanent, captured billions of years ago, and locked in a stable orbit. But we occasionally gain smaller companions, temporary visitors that orbit for a while, before continuing their journey through the solar system. Some beaches whistle and squeak when you walk on them. On certain beaches around the world, walking on the sand produces unexpected sounds, squeaks, whistles, or musical tones. These singing beaches are found in places like Hawaii, California, Scotland, and Japan. The sound occurs only under specific conditions. The sand must be very clean, uniform in grain size, and dry. The sound is produced when the uniform grains rub against each other under pressure. As you step, the grains compress and shear, and if they're all roughly the same size and shape, they vibrate at similar frequencies, creating audible sound waves. The frequency depends on the grain size. Smaller grains produce higher pitches. The sand must be silica-based and relatively spherical. If the grains are coated with organic material, salt, or moisture, the effect disappears. This is why singing beaches squeak most noticeably in dry conditions and fall silent after rain or when wet from waves. Some beaches boom rather than squeak, producing deep, resonant tones when the sand avalanches down dunes. The Mojave Desert's Kelso dunes produce such sounds, sometimes loud enough to hear from miles away. Again, the mechanism involves uniform grain size and specific conditions of dryness and purity. These acoustic sands are geologically interesting because they indicate specific depositional environments and weathering processes. The uniformity required for singing suggests the sand has been sorted by wind or waves over long periods, removing finer and coarser particles until only a narrow size range remains. It's a small wonder, easily missed if you're not paying attention, but when you experience it, the sand squeaking and singing beneath your feet, it's delightfully strange, as if the beach itself is responding to your presence, making music from the simple act of walking. Raindrops are not shaped like tears. In every cartoon, every illustration, raindrops are drawn as teardrop-shaped, pointed at the top, rounded at the bottom. But real raindrops look nothing like this. They're much more spherical, and larger drops are actually flattened on the bottom. Small raindrops, less than 2 millimeters in diameter, are nearly perfect spheres. Surface tension pulls the water into the most compact shape possible, a sphere, and air resistance is minimal at this size, so the sphere remains intact as the drop falls. Larger drops experience more air resistance. As they fall, air pressure pushes against the bottom, flattening it while the top remains rounded. The shape resembles a hamburger bun or a kidney bean more than a teardrop. If drops get too large, more than about 4 or 5 millimeters in diameter, they become unstable and break apart into smaller drops. The teardrop shape does occur, but only in specific situations, when water drips slowly from a surface, clinging momentarily before gravity pulls it away. In this case, the drop elongates, creating a teardrop shape for an instant before it detaches. But once in free fall, it quickly forms into a sphere or flattened sphere depending on its size. This misunderstanding is so widespread that correcting it often surprises people. We've internalized the teardrop image from countless repetitions in media, and challenging it feels almost wrong. But physics doesn't care about our expectations. Air resistance and surface tension shape raindrops, and the result is spherical or flattened, never the classic teardrop we've been shown all our lives. High-speed photography has captured falling raindrops in exquisite detail, revealing their true shapes and even showing how they oscillate and wobble as they fall, constantly adjusting to air resistance and internal forces. They're dynamic, changing shape slightly as they descend. Tiny spheres of water tumbling through air, much more complex and interesting than the simplified teardrops of popular imagination. The longest mountain range on Earth is underwater. When we think of mountain ranges, we picture the Himalayas, the Rockies, the Andes. massive peaks thrust upward into the sky. But the longest mountain range on Earth is hidden beneath the ocean. The mid-ocean ridge system encircles the globe like the seam on a baseball, stretching over 40,000 miles through all the world's ocean basins. This underwater mountain range formed at divergent plate boundaries, where tectonic plates pull apart, and new crust is created. Magma rises from the mantle to fill the gap, cooling into new oceanic crust. This process is called seafloor spreading, and it's constantly creating new ocean floor while old crust is destroyed at subduction zones elsewhere. The mid-ocean ridge is not a single continuous mountain range, but a connected system. The mid-Atlantic ridge runs down the center of the Atlantic Ocean. The East Pacific Rise traverses the Pacific. The Indian Ridge system crosses the Indian Ocean. All are connected, forming a continuous chain of underwater mountains that dwarfs any terrestrial range in length. These ridges rise 6,000 to 10,000 feet above the surrounding sea floor, though they're still miles beneath the ocean surface. Some peaks do breach the surface. Iceland sits atop the mid-Atlantic ridge, one of the few places where the ridge can be seen on land. Along the ridges, hydrothermal vents release superheated, mineral-rich water into the frigid ocean. These vents support unique ecosystems based on chemosynthesis, rather than photosynthesis, with bizarre creatures like giant tube worms, eyeless shrimp, and bacteria that thrive on chemicals. The mid-ocean ridges are among the most geologically active places on Earth, with frequent volcanic eruptions and earthquakes, yet they're largely unseen and unexplored. Mapping these underwater mountains took decades and is still ongoing. Only in recent years have we developed detailed topographic maps of the ocean floor, revealing the true scale and complexity of the mid-ocean ridge system. It's the largest geological feature on Earth's surface, yet most people have never heard of it, hidden as it is beneath miles of water. The atmosphere escapes into space. Earth's atmosphere is not a closed system. Constantly, molecules at the very top of the atmosphere are moving fast enough to escape Earth's gravitational pull and drift off into space. This process, called atmospheric escape, has been happening since the planet formed and will continue as long as Earth exists. At the exosphere, the outermost layer of atmosphere, the air is so thin that molecules can travel long distances without colliding. If a molecule is moving fast enough, above escape velocity, and headed upward, it can leave Earth entirely. Lighter molecules like hydrogen and helium are more easily lost because their lower mass means they reach escape velocity more often at a given temperature. This is why Earth has very little hydrogen and helium in its atmosphere, despite these being the most common elements in the universe. Over billions of years, they've mostly escaped into space. Heavier gases like nitrogen and oxygen are retained much more effectively, their heavier mass keeping them bound to Earth. Earth loses about 3 kilograms of hydrogen and 50 grams of helium per second to space, slow enough that the atmosphere remains relatively stable over human timescales, but significant over geological time. Other escape mechanisms include solar wind stripping, where charged particles from the sun impact the upper atmosphere and knock atoms loose, and polar wind, where ions follow magnetic field lines out into space. Mars experienced much more dramatic atmospheric loss. Being smaller and having a weaker magnetic field, it lost most of its atmosphere over time. What was once possibly a thicker, wetter atmosphere is now thin and dry. Venus, closer to the sun and experiencing intense solar radiation, lost most of its water through atmospheric escape. Hydrogen was lost to space, while oxygen reacted with surface rocks. Earth's magnetic field helps protect the atmosphere by deflecting much of the solar wind, but escape still occurs. Over its lifespan, Earth has lost significant amounts of atmosphere, though replenishment through volcanic outgassing and other processes has maintained balance. The atmosphere is dynamic, constantly being created and lost. Not a static bubble, but a flowing system maintained by multiple processes. And so, we come to the end of our journey. We've drifted through deserts, where sand sings and flowers bloom all at once. We've descended into caves, where organisms glow like stars, and into oceans where rivers flow underwater. We've felt earthquakes reverse rivers, and watched mountains grow millimeter by millimeter. We've learned that forests smell like approaching rain, that clouds weigh more than elephants, that the earth hums a note we cannot hear. All of these facts, all of these quiet wonders, share something profound. They reveal a world more intricate, more alive, and more interconnected than we often realize when we move through our daily lives. Earth is not a static backdrop, not merely a stage for human activity. It's an active, breathing, evolving system, ancient beyond our comprehension, yet changing moment by moment. The planet beneath you is 4.5 billion years old. It has weathered ice ages that covered continents in miles of ice. It has endured asteroid impacts that boiled oceans and darkened skies for years. It has seen continents split apart and collide, creating and destroying mountain ranges. Through all of this, through extinction events and climate catastrophes, life has persisted, adapted, and diversified into millions of forms. You are part of this story, not separate from it. The atoms in your body were forged in stars that died billions of years ago. The water you drink has been cycling through oceans, clouds, rivers, and living things for eons. The air you breathe was produced by ancient cyanobacteria and maintained by forests and plankton. You are made of earth, shaped by it, connected to every other living thing through chains of chemistry and biology that stretch back to the origin of life itself. As your thoughts grow softer and your breath slows, let these wonders settle around you like a gentle blanket. Feel the bed beneath you, the air around you, the quiet darkness of night. You are safe, you are resting, and the planet continues its ancient rhythms beneath you, turning slowly through space, breathing through its forests, humming its low note, singing through its sands. The earth is patient. It was here long before you, and it will be here long after. But right now, in this moment, you are here too, experiencing this brief window of awareness, this temporary arrangement of matter that can think and feel and wonder. Rest now. Let your mind drift like clouds across a quiet sky. Let your muscles relax like tree roots settling into soil. Let your breath slow like the tide retreating from shore. The world will still be here when you wake, still spinning, still glowing faintly in the dark, still humming its ancient song. The horizon will still retreat before you. The wind will still carry stories from distant lands. The soil will still teem with invisible life. And somewhere, a desert will bloom, a mountain will grow a fraction taller, and a cave will glow with living light. All of this continues, has always continued, will always continue. The planet endures, adapts, and surprises us, holding more wonders than we could explore in 1,000 lifetimes. So sleep well, knowing you rest on a world more remarkable than any fiction, more beautiful than any dream. You are, in every sense, a child of Earth, made of stardust, standing on singing sand, breathing air that's traveled the world, held by gravity to a rock that hums beneath your feet. Good night.